Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the type 3 concept illustration problems which are based on the graphs. And you know that in any of the sheet or module of any institute or in any JEE exam or Neet exam or JEE mains or Olympiads, the most asked questions from thermodynamics are of graphs. So this is a very important type as far as thermodynamics is concerned. So, and I'll be going from level 1 to level 3 in this type. So let us start from the question number 1. So you can see that in this question there is a graph which is given between pressure and temperature of a ideal gas, and we have to choose the correct density versus volume graph for this gas. First of all, we know that whatsoever be the process, if volume is changing, density will be definitely changing, and density is equal to mass upon volume. So there is always an inverse relationship between density and volume, and hence this graph would be definitely a hyperbola, rectangular hyperbola. But when volume will be constant, like in process BC, volume is constant and obviously density will be constant. So B and C will be the same points on the graph. So B and C will be the same point on the graph, and as well as in process dA you can see that again volume is constant because this is a straight line plotted between pressure and temperature, and it is passing through the origin. So pressure is directly proportional to temperature when the volume is constant. So again for the process D and dA, the volume and density are constant. So we can say that at points B and C, volume and density is same, and at point A and D, volume and density is same. And therefore from process C to D, pressure is decreasing, temperature is constant, therefore volume will be increasing. So from C to D, volume will be increasing and density will be decreasing. So the correct answer would be obviously option B. Now let's move on the next question. In this question, you can see that there is a graph which is plotted between volume and temperature. This is a straight line graph, and obviously both of the straight lines are passing through the origin as shown in the figure. You can see that we know that PV is equal to nRT, and if this is Y and this is X, then obviously Y is equal to nR by P into X. X is temperature. So you can see that slope of this graph is inversely proportional to P. If M is the slope, then it is nR by P. So the graph with greater slope will have less pressure. So greater slope is of this one. So pressure P2 will be less than P1. So the correct answer is C. Okay, now we move on the next question. In this question, you can see that there is a cyclic process, and we have to find out the work done of this cyclic process. See, we know that this figure seems to be an ellipse, but if it was a circle also, then we know that the area of the circle is pi r square. But if I've seen most of the students doing a basic mistake that they are just taking the radius of volume axis, which is, let's suppose this is delta V. So they are telling that work done is equal to area, and area is pi delta V square. But you should always remember a fact that this delta V square is the square of volume, and dimensionally it is not the work done. So if you are telling this that work done is equal to pi delta V square, then this is a wrong concept. And if you are giving the answer that work done is equal to pi delta P square, then obviously this is also a wrong answer. So when we find out the area and when we find out the work done of a cyclic process, then the work done will be the area, and area will be radius of volume axis into radius of pressure axis. Okay, so the radius of volume axis is this one, and this is V2 minus V1 by 2, and the radius of pressure axis is this one, this is P2 minus P1 by 2. So the work done will be equal to pi by 4 V2 minus V1 into P2 minus P1. Okay, so the correct answer is C. Now we move on the next question. In this question, you can see that a fixed mass of an ideal gas is undergoing this process, which is L to M and then M to N. It is starting from point L and it is ending at point N. So you can see that in process LM pressure is constant, and in process MN temperature is constant. So if pressure is constant, then temperature and volume graph is a straight line which is passing through the origin, and if temperature is constant, then this graph would be a straight line parallel to the volume axis. So the correct answer will be option B, because this is a straight line which is passing through origin, and it shows that temperature is directly proportional to volume, which means that the pressure will remain constant for this line, and from point M to N this temperature remains constant, and therefore it is an isothermal process. Now we move on the next problem. In this question, you can see that a 1 mole of a gas, ideal gas, is subjected to two processes AB and BC, occurring one after another. BC is represented by this equation, PV to the power n is equal to constant. And what we can conclude about the pressure, temperature, volume and work done for these processes. First of all, let us see that obviously in process AB and BC, neither of them is isothermal process, and therefore temperature will not be constant. So A is wrong answer. And in this you can see that pressure at C is less than pressure at B. So this is also wrong answer. And work done in BC is greater than work done in AB. So obviously the area under the graph of AB is greater than the area under the graph of BC, because you can see that the change in volume is same for both of them, but this graph is going in the downward direction, so this area would be less. So work done in BC will be less than work done in AB, so C is also wrong. And you can see that the temperature at A is less than the temperature at B, because at constant pressure volume is increasing, therefore temperature will be increasing. So internal energy at point B will be greater than the internal energy at point A. So D will be the correct answer. Now we move on the next question. In this question, you can see that the graph between temperature and volume is a straight line, but obviously this straight line is not passing through the origin if it is extended. It is cutting the y-axis or the temperature axis at some positive point. So what we can say about the relation between pressure and volume? So many of the students are committing a mistake in this question, that if temperature is directly proportional to the volume or volume is directly proportional to the temperature, then they are saying that pressure will be constant. This is correct, but this is only correct when the graph between temperature and volume is a straight line and it is passing through the origin. Then pressure will be constant. But it is not a straight line which is passing through origin. So you should not make a mistake that pressure will be constant. So what you should do, you should write down the equation of temperature in terms of volume, that T will be equal to slope is 1, volume is V, plus some constant C. And you know that PV is equal to nRT. So PV is equal to N R and T is V plus C. So P is equal to N R 1 plus C by V. So you can see that pressure is inversely proportional to the volume, and therefore this is a rectangular hyperbola. So the relationship of the pressure and volume will be hyperbolic. So A is the correct answer. Now we move on the next question. In this problem, you can see that there are two thermodynamical processes. This is a straight line which is passing through origin, and this is a rectangular hyperbola. You can see the coordinates of temperature and volume in both of them, and we have to find out the ratio of work done in these two processes. Now the first process can be seen that it is a isobaric process. Pressure is constant, and for isobaric process the work done will be P delta V. So work done will be positive because it is a expansion, and pressure at any point will be same. So pressure at this point will be P will be equal to nR T divided by V naught into delta V. Delta V is obviously V naught. So work done will be equal to nR T naught for this first process. And for this second process, the work done can be calculated, but it is a rectangular hyperbola, which means that temperature is inversely proportional to volume. And we know that T is equal to PV by NR. So PV is inversely proportional to volume. So PV square is constant, which means that this is a polytropic process and N is equal to 2. And work done in polytropic process is R delta T upon gamma minus 1. And this is a expansion process, so work done will be positive. So work done W2 will be equal to R delta T will be T naught by 2, and instead of gamma, because this is for adiabatic process, so instead of gamma we would use N for polytropic process, so this is N minus 1. So work done will be equal to R T naught upon 2, because N minus 1 will be equal to 1, and N is the number of moles. This N is the number of moles, and this is the polytropic constant. So work done will be nR T naught by 2. So the ratio of work done W1 by W2 will be 2:1. So the correct answer will be B. Now let's move on the next question. In this question, you can see that this is a PV graph, and an ideal gas is being compressed from a volume 15 meter cube to 12 meter cube adiabatically, and then it is being compressed from 12 to 3 meter cube isothermally. There are 2 moles of the gas, and we have to find out the total heat supplied to the gas. We know that in adiabatic process, heat supplied will be 0. So we just have to calculate the heat supplied in isothermal process. And obviously in isothermal process delta U is 0. So the heat supplied to the gas in isothermal process will be equal to work done by the gas. And as we know that the work done by the gas is negative because it is compression, so we can say that the heat supplied to the gas will be equal to minus of work done mod magnitude of work done. So heat supplied will be equal to minus of nRT ln V final by V initial. See, we have already used this negative sign. Now we have to write down the positive magnitude of work done. Therefore, this would be minus nR, and temperature will be PV upon nR, ln V final by V initial, and this is not V final by V initial. I can say that if I have to write down the magnitude of work done, and obviously the magnitude would be positive, so it would be the greater volume upon a smaller volume. The greater volume between this range will be 12 and the smaller volume will be 3. So this will be equal to minus PV ln 4, and heat supplied would be negative, and PV will be the value of pressure and volume product at this point or this point, it would be same. So PV will be minus 400 into 12, and this is in standard unit also, and this is ln 4, which is 2 into ln 2. So it would be minus 6653 joule. So the correct answer will be C. Now let's move on the next question. In this question, you can see that this is a graph plotted between density and internal energy of the gas. Now density is obviously mass upon volume, and this graph is a rectangular hyperbola, which means that density is inversely proportional to the internal energy, and by this we can say that it is C by V, and in fact this is U, and U we know is the temperature only, so we can say that volume is directly proportional to the temperature, so pressure will be constant. So this graph will be a isobaric process, and obviously you can see that if the volume in going from A to B, volume increases, the volume is increasing because density is decreasing. You can see the temperature of the gas in going from A to B increases, and therefore delta U will be positive and dW will be positive. So dQ will be positive and heat supplied to the gas will be positive, which means that gas absorbs the heat. A is incorrect, B is correct. Process A to B is adiabatic, this is also incorrect. This is isobaric process, and temperature of the gas increases from A to B, decreases from A to B, it is also incorrect. So the correct answer is only B. Now we move on the next question. In this question, you can see that this is a PV graph, which is a circle, and this is plotted for an ideal gas. If we start from point A, then process AB is a isothermal process and process AC is a adiabatic process. So we have to comment about the heat given to the gas in different processes, about their sign, which is positive, negative, 0, or it can't be said. So first of all, let us see that we know that from A to C, if we move from A to C, let us draw this circle, or yeah, this is process AB and this is process AC. Let me draw again. This is AB and this is AC and this is D. So you can see that obviously in this process AC, the work done will be the area bounded between this curve and volume axis, this area, and let us suppose that this area is W1. So the work done in this process will be positive because it is expansion. So the dQ in AC will be 0 because AC is a adiabatic process, and dQ will be equal to du plus dW. So du will be equal to minus of dW, and that is minus W1. Now when we are going from A to C but from circle like that, So you can see that an additional amount of area is involved. This is the additional amount of area, and let us suppose that this is W2. So while going from A to C via circle, the total area will be this one, this area, W1 plus W2. So work done will be W1 plus W2, and heat supplied in A to C from circle will be equal to du plus dw. Now du is not a path function, it is a state function, and final and initial points are same, therefore du will be same. Du will be minus w1 and dw will be w1 plus w2. So this heat supplied would be positive w2. So the first option A matches with P. Now heat given to the gas in going from B to C along the circle. Now when we are going from B to C along the circle, along this path, then you can see that this graph is going down, so pressure is decreasing, and this graph is going in the backward side, so volume is also decreasing, which means that PV is equal to nRT, and P is decreasing, V is decreasing, therefore T will be decreasing, temperature will be decreasing, and therefore delta U will be negative, and therefore if volume is decreasing, work done will be negative, and therefore heat supplied will be negative, which means that the heat supplied will be negative, and from B to C the correct matching will be Q, and heat given to the gas in going from C to D along the circle. Now when we are again moving from C to D, you can see that D point lies lower than C, therefore we can say that pressure of the gas is decreasing and volume of the gas is also decreasing. So temperature will be decreasing, and du will be negative, dw will be negative because it is compression, volume is decreasing, and dq will be negative. So the correct matching will be Q. Now we move on the next question. In this question, you can see that 1 mole of an ideal gas is carried through this thermodynamical cycle AB, then BC, and then CA. This cycle consists of one isochoric process, one isothermal process, and one adiabatic process. This is isochoric, this is isothermal, and this is adiabatic, due to the fact that the slope magnitude of adiabatic is greater than the slope magnitude of isothermal, or we can say that the adiabatic graph is steeper than the isothermal graph. So we have to find out the value of gamma, as well as we have to choose the correct option from these two. So BC is adiabatic, so BC is isothermal, so this would be the wrong option, C. And AC will be adiabatic, so AC process will be adiabatic process, so this would be the correct option. And we know that you can see that if we apply the equation for C and B, and we know that BC is isothermal process, so for isothermal process P1 V1 is equal to P2 V2. So P1 is 3 P0 and V1 is Vc is equal to P2 is P0 and V2 is V0. So Vc will be equal to V0 by 3. Now we will apply the adiabatic equation for Ca, adiabatic process. So we know that 3 P0 into V0 into Vc to the power gamma is equal to P0 by 2 into V0 to the power gamma. So 3 P0 into Vc, Vc is V0 by 3 to the power gamma is equal to P0 by 2 into V0 to the power gamma. So cancelling out this P0 with P0, so this would be 3 to the power 1 minus gamma into V0 to the power gamma is equal to V0 to the power gamma upon 2. So you can see that 3 to the power gamma minus 1 is equal to 2, and if we take log both the sides, then this is gamma minus 1 ln 3 will be equal to ln 2. So gamma minus 1 will be equal to ln2 by ln3, and gamma will be equal to ln2 by ln3 plus 1. Now to match the answers, let us write down 1. Let us use the next page. So gamma is equal to ln 2 by ln3 plus 1, and 1 can be written as ln3 by ln3. So gamma will be equal to ln2 by ln3 plus ln3 by ln3. Now taking ln3 common from the denominator, it would be ln2 plus ln3 upon ln3. And you know that log a plus log b is log a into b, so it would be ln6 by ln3. So gamma will be equal to ln6 by ln3, so the correct answer will be A. Now we move on the next question. In this question, you can see that there are 2 moles of an ideal monatomic gas which is going through this process. This is a cyclic process, and the number of moles of the gas are 2, and it is very important to note that this is a PU graph. This is a cyclic process which is plotted between pressure and internal energy. So we have to find out the work done in the cycle, and obviously we cannot say that the work done in the cycle will be the area of the cycle, because this is not a PV graph. So we have to first of all find out the temperature T2 at this point and temperature T1 at this point. So U2 is 36 calories, so 3600 calories, so it would be equal to 15120 joules. So U2 will be equal to 15120 joules, and U2 will be equal to NR into T2. So T2 will be equal to U2 upon NR. So T2 will be equal to U2 is 15120 upon N is 2 and R is 8.14. So it would be equal to almost T2 will be equal to 7560 upon R. Okay, and now we find out the T1. So T1 will be equal to, you can find out T1 by U1 by NR, and therefore T1 will be equal to, U1 is 1800, so 1800 calories is 7560 joules divided by 2 into R. So it would be equal to 3780. Okay, 3780 by R. So we can say that T2 is equal to twice of T1, first of all. Now let us see that if pressure is 4 atms, so it would be 4 into 10 raised to power 5 Pascal, and this is P, so this is 2P. Now let us separately find out the work done in all the processes. So work done in AB. Now AB is a isobaric process, and in isobaric process pressure, if pressure is constant and temperature becomes double of the initial temperature, then volume also becomes double. So work done will be P delta V, and work done in A to B will be P delta V will be V, 2V minus V, and we know that PV is equal to nRT, and the temperature of this gas will be at this point, because we have considered that V is the volume at this point and 2V is the volume at this point. Okay, so it would be nRT1. N is 2, and we know that nRT1 is equal to U1, and U1 is 7560. So it is 7560 joules. Now in process CD, if we find out the work done in process CD, then you can see that process CD is a isobaric process, and the volume is decreasing because temperature is decreasing. So what we can say that if in isobaric process work done would be obviously negative because this is a compression, and if the volume at this point is again, let's suppose V1, and at this point it would be 2V1. Okay, so the work done would be P2 into 2V1 minus V1 with a negative sign because it is a compression. So it would be minus P2 into V1. P2 is the pressure at this point, this is P2, and V1 is the volume at this point. So you can see that P2 V1 is the net work done, and it would be equal to NR. Again, the temperature at this point is T1. So NR T1 with a negative sign. So work done in C to D will be again NR T1, which is U1, and U1 is 7560. So it is minus 7560. So work done in A to B plus work done in C to D is 0. Now let us see the work done in B to C. In B to C, you can see that this pressure is decreasing at constant temperature, therefore volume will be increasing because this is an isothermal process. So B to C is an isothermal process, and work done in isothermal expansion because pressure is decreasing and temperature is constant, so volume will be increasing. So work done will be positive, plus nRT2 ln. Now you can see that pressure has become half, so volume has become twice. So if volume at this point is VB, then volume at this point will be 2VB. So we will write down ln 2, and we know that nRT2 is equal to U2, which is 15120. So work done in B to C will be equal to plus 15120 ln 2, and work done in D to A. In process D2A, it is isothermal process and pressure is increasing, so volume will be decreasing. So work done will be negative, minus of nRT1 ln 2 again. So work done in D2A will be equal to minus of this is nRT1 is 7560 ln 2. So the net work done in the process will be equal to 15120 minus 7560 ln 2, and it would be 7560 ln 2 joules. So if we have to find out the work done in joule, then it would be equal to 7560 ln 2 joules, and the value of K will be equal to 75.6. If we use 7560 is equal to K into 10 raised to power 2. So K will be equal to 75.6. Okay, now we move on the next question. In this process, in this problem, you can see that there is a sample of 3 moles of an ideal gas that is undergoing a cyclic process A, B, C, A, and a total of 1500 joules of heat is withdrawn from the sample of this gas in this process. The work done during the part BC will be this one. We have to find out the value of P. See, first of all, it is not mentioned in the question that BC is a adiabatic process or isothermal process. So we could not consider it adiabatic or isothermal or any specific process. So we could not use the process equation to find out the value of work done in part BC. Indeed, what we have to do is the fact that we know that the delta U in the complete cycle will be 0 because it is a cyclic process, and dW will be equal to the heat supplied. But in this process, a heat is 1500 joule heat is extracted from the process, so the work done will be equal to minus of 1500. This minus denotes the fact that the net work done is negative and that work done on the gas is more than work done by the gas. Now we know that in process C to A, the work done is 0 because it is a isochoric process, and in process work done of process A to B plus work done of process B to C is equal to 0 because net work done in fact it is equal to minus 1500 joules because net work done is minus 1500 joules. Now AB process is a isobaric process. So it is a isobaric process, and in isobaric process the work done will be equal to P delta V, and you can see that if this is V1 and if this is V2, so we can say that it would be equal to PV2 minus PV1. Okay, this will be the work done. So work done will be P2V2, in fact PV2 minus PV1, and PV2 is equal to the nRT2 and PV1 is equal to nRT1. So work done in this process A to B will be equal to N is 3, R is R, T2 minus T1 is 300. So it would be equal to 900 R, and volume is increasing, so it would be positive. And the total R value of R is 25 by 3, so it is 25 by 3. So it would be equal to 300 into 25. So work done will be equal to 7500. Now the net work done in BC will be equal to minus 1500 minus 7500. So it would be minus 9000 kilojoules. In fact 9000 joules, which can be written as minus 9 kilojoules. So the value of P will be equal to 9. Now we move on the next question. In this question, you can see that 1 mole of a monoatomic ideal gas is taken along this cyclic process, and the process involved in this complete cycle is isobaric, isochoric, adiabatic and isothermal. So obviously this process will be isothermal, this process will be adiabatic, this will be isobaric, and this will be isochoric. Now we have to match the work done in the different processes. So first of all, let us see the work done of GE. But before finding out that, we have to find out the volume at G and the volume at H. And to find out the volume at G, we know that Fg is a isothermal process, and we know that P1 V1 will be equal to P2 V2. So P1 is 32 P naught, V1 is equal to V naught, and P2 is P naught, and V2 is Vg. So Vg will be equal to 32 V naught. And similarly, if we apply the work done, if we apply the equation for F to H then we know that FH process is a adiabatic process, and in adiabatic process the equation of the process is P1 V1 to the power gamma is equal to P to V to the power gamma. This gas is a monoatomic gas whose degree of freedom will be 3, so gamma of this gas will be 1 plus 2 by 3, which will be equal to 5 by 3. So P1 is 32 P0 and volume is V0 to the power 5 by 3, and that is equal to P2. P2 is again P0. Volume is VH to the power 5 by 3. So VH will be equal to 32 to the power 3 by 5 into V0. So VH will be equal to 8 V0. This is 8 V0. Now work done in G2E. Work done in G2E, and you can see that these are the magnitudes of work done because they are all positive. So we just have to find out the magnitude of work done, and apart from that, if we consider the sign also, so we can see that GE process is a isobaric compression process, and hence the work done will be negative, and the work done value will be equal to P delta V. So if we find out the work done in process G to E, then it would be P delta V. We are calculating the magnitude only. So P delta V, P0 is the pressure, and delta V will be equal to 32 minus V0. So it will be 31 V0. 31 V0. So it would be equal to 31 P0 V0. So the correct matching of P will be fourth. Now GE process, now we have to find out the work done in GH. So work done in GH will be also isobaric process, and pressure is P0, and the change in volume from G to H will be equal to 32 V0 minus 8 V0. So it would be equal to 24 V0. So it is 24 P0 V0 work done in GH. And work done in FH. So in FH process, you can see FH is a adiabatic process. So work done in FH will be equal to NR delta T upon gamma minus 1. Sorry. So N will be equal to 1, and R is R. Delta T in this process, you can see that delta T could be calculated, but we can also calculate it as P1 V1 minus P2 V2 upon gamma minus 1. Okay. So P1 V1 is 32 P0 V0 and P2 V2 is 8 P0 V0. So it is 32 P0 V0 minus 8 P0 V0 divided by gamma minus 1. So it would be 5 by 3 minus 1. So it is equal to 24 P0 V0 upon 2 by 3. So into 3. So it will be equal to 36 P0 V0. So the correct answer of this G to H, in fact we have already calculated the value of work done in G to H, which is 24 P0 V0. So it would be 3, which is matching with option Q. And in F to H, the work done will be 36 P0 V0. So it would be, there would be correct matching of option R with 2. And in F to G, F to G is an isothermal process. So work done in F to G will be, this is F to G, it would be nRT ln V final by V initial. So N is 1, R is R, and T is the temperature in this process. So temperature in this process will be 32 P0 V0 upon R. So it would be 32 P naught V naught upon R, and volume will be equal to 30. Final volume is 32 V naught, initial volume is V naught. So it will be ln 32, and ln 32 can be written as 5 ln 2. So 5 into 32 is 160 P naught V naught ln 2. So the correct matching of this option will be option 1. Now we move on the next question. In this question, you can see that this is a graph which is plotted between volume and temperature. And there are two states, state 1 and state 2 of the ideal gas. We have to specify the fact that at which state the pressure is greater. So it is very important to note that if we extend this graph further, then you can see that this graph will cut the y-axis at bottom point. So obviously the intercept of this graph will be negative and slope will be positive. So the equation of this graph will be y is equal to mx minus c. So instead of y it is v. So v will be equal to m into t minus c. Now pv is equal to nRT. So p will be equal to nRT upon v. So p will be equal to nr upon v, which is mt minus c, and this is t. So p will be equal to nr upon m minus c by t. So you can see that if t increases, this complete term decreases, and this complete term increases, and p decreases. So which means that if t increases, pressure decreases. Hence we can say that the temperature at 2 is higher than temperature at 1. Therefore pressure at 2 will be lower than the pressure at 1. So we can say that higher pressure will be at state 1. Now we move on the next question.